So good afternoon, everyone. Welcome back to Math 122. Today we're going to keep on with our discussion of Chapter 3, where we are learning, broadly speaking, derivative rules, okay? How to find the actual derivative function, okay? And how to use it. So you have some homework assignments. I think one has already been due, so I'll erase that one. And then 2.5 is the last one due before break. It's due tomorrow night. We did 2.5 a while ago, so you could have already finished that or finish it today or whatever if you're trying to leave for spring break. 3.1 and 3.2 are going to be due on the Monday following spring break. So my recommendation would be to take care of those before spring break so that you don't have to do them on the Monday after spring break, but you could do them then too. Quiz 5 is going to be today, so let me set an alarm to do the quiz. So that alarm needs to be, we end at 4:05, so I need to set the alarm for 3:50. Well, we'll do 3:48. I have 2 minutes to pass it out, and y'all have 15 minutes to do it. No, not AM, PM. All right. So office hours are the same as always. Math Tutoring Center, same as always. SI, same as always. Are there any administrative questions, comments, or concerns before we start in on content for today? Yeah.
Do you have a quiz after the spring break?
Good question. Does anybody know off the top of their head? Probably. I think we usually have a quiz on every Thursday that we don't have an exam. But let's double check it. So we got the syllabus here. So that will be March 16. Yes, we have a quiz. Okay. Any other questions before we start? Okay, then let me quickly remind you what we've been talking about so far with Chapter 3. So far with Chapter 3, we've been talking about derivative rules. So up until Chapter 3, our only way to compute derivatives was to do average rate of change over very small intervals, and even then it only gave us an approximation of the derivative. And what we're now learning are some rules for finding derivative functions that give us an exact result, okay? And not only is it an exact result, it's pretty much way easier than doing the average rate of change business. Okay, so we're gonna use these derivative functions to find the derivatives of functions and to use those derivatives to understand how their parent function is changing, okay? So derivative and rate of change are together as concepts, okay? The rate of change of a function is the derivative of that function, and the derivative of that function is the rate of change of that function. Okay, so the rules which we've learned so far is how to do the derivative of a handful of functions. And we're gonna learn more rules today for doing different functions, okay? So the functions that we know how to do the derivative of so far are a constant, okay? Derivative of a constant is just 0. That's because constant functions aren't changing. The rate at which a constant function is changing is 0 because it's not changing. The rate at which a linear function is changing is perfectly encapsulated by the slope, right? That's the steepness, okay? The rate at which you are changing the height of the function for a linear function is just the slope. We learned that the derivative of a sum or a difference of two functions is just the sum or the difference of the derivatives of those functions. Okay, so the derivative of a sum is the sum of the derivatives. And an extension of that is, of course, that we can pull any constant that we want out of the derivative operator in the sense that the derivative of a constant times something is just the constant times whatever the derivative of that something is. Okay, so we can pull the constants out. So then we did some examples and we saw the power rule. That was the last one we learned, which says, look, if you want to do the derivative of something like x to the n, where n is a number, yes, where n is a number, not 0, then the derivative will be n times x to the n minus 1. Okay, n times x to the n minus 1. I suppose it kind of still works with n equals 0, but we won't say anything about that. Okay, so what is the idea? You take the power down front and you subtract 1 from that power. Okay, so for x to the 8, it becomes 8x to the 7th. For x to the minus 3, it becomes minus 3 times x to the minus 4. Okay, and we can do all sorts of other stuff with like square roots, right? We can subtract 1/2 from 1/2 to get negative 1/2. Okay, so x to the 1/2, its derivative would be 1/2, because that's the power, gets multiplied down. Take away 1 from 1/2, then you have 1/2. Okay? So what this tells us, okay, is what is the actual slope of the tangent line, okay? So we can take this new derivative function, okay, and have an actual closed form formula for it, which tells us, okay, its job is you plug in a number, the derivative function's job is to spit back at you the slope of the parent function. Okay, so for f of x equals x squared, whose graph is shown in green, its derivative is 2x. So if I plug in f prime of 1, that's going to tell me the slope of the tangent line to the function f of x equals x squared when x is equal to 1. In other words, it's the slope of this blue line. Okay, so this tells us basically how the function is rising or falling at a given point and how steeply. So that's the whole point of the derivative. Any questions on what we talked about last time? Okay, it doesn't seem like there are, so let's move on. Okay, so today we're going to talk about section 3.2. So we're going to skip the warm-up. We always skip the warm-up, almost always. And we're going to do some new rules. Okay, some new rules. So the next 3 that we're going to learn are seen here on the screen. We're going to learn derivative of an exponential function and derivative of e to the kx, which is just a different type of exponential function, really. And we're going to learn the derivative of the natural logarithm. Okay, so those 3 rules go as follows. The derivative of a to the x, where a is any positive number, is a to the x, again, times ln of a. Okay, times ln of a. Okay, so we just rewrite the same thing, and then you multiply by the natural log of whatever is the base. Okay? So for example, let me do one more rule, and then we'll do the first example. Or maybe I'll just give you a quick one. For example, the derivative of 5 to the x is 5 to the x times ln of 5. Okay? All right, so that's a to the x. And for e to the kx, we can use the previous rule to figure out what this is going to be, quite simply by doing the following. Well, if I want to do the derivative of e to the kx, I can rewrite that as the derivative of e to the k, which is just a number, to the x. So I can use the previous rule where I let a just be this number e to the k. Okay, e to the k is a. So I'm going to write, using the previous rule, e to the k to the x times ln of e to the k, which is just k times e to the k, x. k times e to the kx. Okay, so that's just because ln of e to the k is k. All right, so a special case of that. So special case. Maybe I use a different color. Special case of that is the easiest derivative ever to do is the derivative of e to the x. Well, this is e to the kx where k is 1. So I do 1 times e to the 1x, which is just e to the x. So the derivative of e to the x is e to the x. So it's a function whose own derivative is itself. In other words, its height is the same as its slope at every point, okay? If you have an exponential function e to the x, the slope here is the same as the height, okay? That's the whole special thing about e to the x. Okay? So the slope is the same as the height. And in fact, that's how we define the number e. It's the number such that the exponential with that base causes the slope to be the same as the height, i.e. causes the derivative to be the same as itself. Okay? So that's where the number e actually comes from. So we saw a to the x and e to the x. I think we're ready to do problem 1a in light of these two new rules plus another rule. What other rule besides these two am I going to need to use to take the derivative in part A? Well, two other rules, really. What are the two other rules that I need besides the a to the x rule and the e to the kx rule? Maybe we, yeah.
The constant and the sum.
Yeah, that's it. The constant rule and the sum rule, right? Okay, why do I need to use the sum rule? Because there's a sum. Why do I need to use the constant multiple rule? Because both of these two functions, I know how to do the derivative of this one using this rule, and I know how to do the derivative of this one using this rule, but they're both being multiplied by something. So I also have to remember the constant multiple rule, which says that those constants are just going to hang out. Okay? So to do this derivative, we know that we can just do the derivative of each piece and then add them together. That's the that's the sum and difference rule. And then the constant multiple rule says that, look, the derivative of 2 times this function is just going to be 2 times whatever is the derivative of 3 to the x, which we just learned will be 3 to the x times ln of 3. And now we add, and what is the derivative of 5e to the x going to be? Well, it's going to be 5 times whatever the derivative of e to the x is, which the derivative of e to the x is just itself. So it turns out the derivative of 5e to the x is also 5e to the x. Okay, so that's our two new rules seen in action here. How do we feel about that one? Let's have some thumbs really, really high. Would you be able to do that on the quiz next Thursday? Down if not, and up if yes. Not next Thursday, but the one after that. Okay. Do you have a question?
Yeah. Why isn't the 5e to the x like the ln to the 5?
Okay, so why is there no ln of 5 here, was the question. So the answer is because the rule says the derivative of a to the x, right, is a to the x times ln a. But the 5 here is not part of the base. The 5 here is not part of the base. The base here is e. Okay? So the base here is e. So if you use the rule in part 1, you would get e to the x times ln of e. And ln of e is 1. Does that answer your question?
Yes.
All right. Any other questions? Yeah, Jake.
If you multiply like the 2 and that derivative, you will get it's like you add it and plus it, which is a constant. But multiplying the derivative.
Sorry, could you repeat that but louder?
So like in D, like so like 5, you just get rid of that 5. And then like problem B, it's like you're adding it.
You're talking about problem D now.
Yeah, but I'm just like, for example, like why would you keep that 2 if you multiply it?
Aha. Okay, yeah, it's because it's multiplied, not added. So the only case in which the constant goes away is when it's by itself. But here the constant's being multiplied times a function. So the constant's going to hang out, and then we're going to write the derivative of whatever that function is. Yeah. Does that answer your question? These are good questions. Any more questions? Yeah, Alex.
So if it's added, you just get it.
If it's
If it's added, it's going to
yes, if you just add a constant, then the sum and difference rule says that the derivative of 5 plus all this jazz will just be the derivative of 5 plus the derivative of all of this stuff, right? But later on, we're going to learn another rule that says that it's not true that if you multiply two functions together and you take their derivative, it's not the same as the multiplication of the one derivative with the multiplication of the other. We have to use a special rule called the product rule. But we're going to get to that maybe later today or tomorrow or on Tuesday after spring break. Okay, so in short, yes, it's different because it's being multiplied. We can only get rid of a constant using the derivative rule if it's by itself. All right, these are good. I think we should do some more examples to see how this is working out. Okay, so here I'm doing derivative of f of x equals 15 e to the 1/3 x minus 17x. To do the derivative of the first part, I know that I just need to write the 15, since it's being multiplied, is going to hang out. And then I need to write, in this blank, I need to write the derivative of e to the 1/3 x. What do I get when I do the derivative of e to the 1/3 x? So what should come in my blank here? E to the 1/3 x, need to do the derivative of it.
1/3 times e to the 1/3 x.
Yeah, 1/3 times e to the 1/3 x. So that we just get 1/3 e to the 1/3 x. Sorry, Olivia, it's just because you already answered one. Okay, so next up we still need to do the derivative of the other part, right? So I write a minus sign, and in this blank needs to come the derivative of 17x, which, since 17x is a linear function, its derivative is just the slope of that linear function, which for this one is 17. So we subtract 17. Okay, so if you wanted to clean it up a little bit, you could write 15/3 e to the 1/3 x minus 17. Questions on part E? Yeah, Alex.
Can you just use add or subtracting?
Sorry?
Don't if you're just adding or subtracting, you got rid of it.
Only if you're adding or subtracting a number. But here, what are we subtracting? 17x is not a number, it's a function. Okay? It's a function, and it's a linear function. Okay? So the derivative of a constant, okay? A constant is like 14. Right? Just a number by itself. But I say constant in opposition to function. By constant, I mean just a number. No x's involved at all. By function, I mean stuff with x. So derivative of a constant, if there's no x at all, is just 0. But the derivative of something with x, we have to use the respective rule depending on the type of function that it is. So in my example here for part E, I have the difference of two functions. The first function is an exponential function, so I have to use the exponential rule. The second function, which I'm subtracting from the first, is a linear function. So to do its derivative, I have to use the derivative rules for linear functions. Okay, I promise once you do some more practice with these, you'll get the hang of this really quickly. Okay, let's do one more just for good measure. 2e to the minus 1.9x. Okay, now we're going to play a game here. I'm going to be the student and you're going to be the teacher. And I'm going to show you my work. And I'm telling you up front that my work is wrong. And you're going to give me a bad grade, but I'm a student, so I want to know what I did wrong. So you have to tell me why I got a bad grade. Okay? Does that sound like a fun game? No?
This sounds weird. I don't know how you do it.
Okay, let's do it. So, I see I have 2e to the minus 1.9x, and then I've got a minus 14. So I know that the minus 14 is going to go away, because that's the constant rule. And I know that this function's being multiplied by 2, so the 2 is just going to hang out. And then for this one, I have something to a power, so I need to multiply down by the previous power, so that's 1.9x. And then I need to do e to the, and I need to make this power 1 less than it was before, so I'll just subtract 1. Am I right? No, I told you I'm not right. But why am I not right here? What mistake have I made? Not supposed to bring x down?
And then not supposed to subtract by 1.
Yeah, in other words, I'm not supposed to use the power rule. Why not? Because I can only use the power rule when my function is a power function. And this is not a power function. E to the minus 1.9x is not a power function. What kind of function is it? It's an exponential function. Okay, so I like doing this example here to just highlight, okay, the idea behind the rules is that you can only use the rule when your function matches the criteria for the application of the rule. Okay? So, in particular, we learned that the derivative of x to the power n is equal to n times x to the n minus 1, where n is a number and x is a variable. Okay? It's completely different if you switch to a number to a variable is not the same as a variable to a number. Okay? So this is a completely different type of function. I can only apply the rule when I have the right kind of function. So the first thing we have to do is identify, like, okay, what kind of functions do I have? What rules do I know for those types of functions? And then go ahead and apply them in the correct places, in the correct time, in the correct circumstance. Okay? So let me show you the way that we would actually do this problem. So instead of using the power rule for this one, we'd do the following. We can still get rid of the 14, but then we would say the 2 is going to hang out. The rule for e to the kx says, look, it's k times e to the kx. So you multiply down by whatever is the factor of k, and then you rewrite the exponential. So I'm going to write negative 1.9, and then e to the negative 1.9x. Okay? So we have to identify and be a little bit careful about what rules do I need to use. So I like to help students when they come to my office hours and they say, I don't know why I got this wrong. It's because sometimes people feel like they just want to get going with the problem, right? And so they say, I'm going to apply this rule. But they don't stop to think, is this the correct rule to be using, right? So it's best to sort of take a step back before you start in on your calculations and say, okay, what rules do I actually need to be using to do this problem? Okay? All right. Any questions on these examples? More questions on these examples? Okay, then let's see one more, which is the derivative of ln of x. So the derivative of ln of x is equal to 1 over x. Okay? And I just want to be emphatically clear that this only works in the one direction, okay? So if you see derivative of 1 over x, this is not going to be natural log. What rule would we use to do the derivative of 1 over x? The power rule, because you can write 1 over x as x to the minus 1, i.e. variable to a number. That's when we use the power rule, okay? So it works only in this direction, okay? The derivative of the natural log function is 1 over x. Okay, why is that true? I can show you kind of a picture to help you see what that is really saying. So let's look at the graph of the natural log function. The graph of the natural log function looks something like this. Okay, where it passes through the point 1, 0. Okay, so what is up with this natural log function? Well, this is ln of x. And it turns out as you send, let's say x naught here, okay, out to the right, then what is the derivative supposed to tell us? The derivative is supposed to tell us what is the slope of the tangent line. So f prime of x naught is 1 over x naught is the slope of this line right here. Okay? So why does this make sense? Well, as x gets larger, what happens to 1 over x? When x gets larger, the denominator is getting bigger. So the whole number is getting smaller, right? Which we see that in the graph of the natural log function. What's happening to the slope as we move to the right? It's becoming less and less extreme. As x gets larger, the slope is getting smaller, right? We can see it in the graph. Okay? So that's hopefully some motivation for why you can believe this to be true. But in terms of this class, we'll just be measuring whether or not you are able to apply the rule, right? So if you want, you can just memorize it. So these are our 3 new rules for this section. Wait, do we have another one for this section? I think, no. Those are the 3 new rules for this section. So let's see really quickly how that would work with part A of problem 2. All right, so I need to find the derivative here, and I'm going to use the following rules. I'm going to use the sum and difference rule because I have differences and sums. So I'm just going to do the derivative of each summand. Okay? So let's start with the first one. 5 times ln of t. I can use the constant multiple rule to say that the 5 is going to hang out. And then what I need to write in this blank will be the derivative of ln of t, which we just learned is 1 over t. Okay, now comes a plus sign. And we need to write down the derivative of 7e to the t. Okay, 7e to the t. So, again, the constant multiple rule says that the 7 is going to hang out. And then what is the derivative of e to the t? It's the easiest derivative of them all.
E to the T.
Just e to the t. And then minus, now we got a weird one. We haven't seen this one since last class. 4t squared. What do I do with 4t squared?
2 out front, drop the exponent.
Yeah, power rule. So the 2 is going to come down front and multiply. So first of all, the 4 hangs out, and then the 2 comes down. And what happens to the power? We subtract by 1, so it becomes t to the 1, which is just t. All right, Alex, what's going to happen with the last part? Forget about it, exactly. It's 0, okay? Minus 0. So the last part, because it's just a number, its derivative is 0. But all the other things, they have t with it, so we got to use the right rule. Okay? All right, any questions on that example? All right, if not, then we're going to do a group work. So get in your groups, and we're going to work on problem number 4 here. Okay, so very business-minded money problem. So I'll be walking around, Jacob will be walking around. Just raise your hand if you need a little bit of help or some individual attention.
So we start at 2,000. There's continuously, so it's T to the KT, right? It's involved.
B to the 0,
It's 0, right?
0, 0,
0, yeah, okay.
What do we got so far?
Oh, I'm sorry.
Sorry, yeah, exactly. So for the first part, right, we're just checking like how much is like left in the bank account after however many years, right? Yeah, exactly. So I'm just plugging in, and then how do I do that prime and 20, right? Derivative of that function, and then plug in 20, right? And then we got to interpret too.
No, I found
Really right
it.
track.
I found it was good enough for me. Okay, so now, all we gotta do is organize the equation. So we would do,
So we got $2,000 deposit earns 8%, right? So we got to use our compound interest. Remember that one for continuous interest? Okay, so it's P of T. Sorry. No, I think that was a couple for. So P of T is just equal to our P naught, right, times e to the kt, where our P naught is our original investment. So what's our original investment? Yeah, so we're gonna put that in for P naught. So it's going to equal 2,000 where we see P naught. And then what's our interest rate? 8%, right? So how do we get K from 8%? Okay, so percent, roughly speaking, per means divide. And what does cent mean? What number comes to mind when you think cent? 10, 100, right? 100 cents in a penny, or 100 cents in a dollar, right? So means we divide by 100. So our K is going to be 8% divided by 100, which is 0.08. Okay, so that's what we're going to put in here. So we have E and then 0.08. Yeah.
Where do you go for straight rate?
So this
Yeah, I have to
expresses
go
like
out to
how
my
much
sister's
money we
baby
have
shower
left
this
in our
weekend,
bank account
and then
after
we're going to
2 years,
Toronto
whatever,
to a home
2 years, and then
So it's
we multiply all this out on our calculator.
I'm like excited because it's fun,
So if I
but
wanted to
like
find
it's
out
gonna
what
be
it
cold.
is,
Because
At
it's
my
a
house,
winter storm.
yeah, at my house,
then I'm just gonna put in 20.
like my mom was
And
FaceTiming
that's
me,
gonna tell me how much money I have after.
Yeah, my mom just moved her flight to go
37
there's a winter storm.
Yeah, I need to go in Toronto. I might try to do it this summer when I go down.
It's really fun, and this is my first time going, like actually nice, so I'm
It's
Our
I don't know, it's like an hour and a half drive to Niagara Falls.
E to the KX rule.
Like a little drive. Definitely like to go there.
yeah, I have no idea how we're gonna like get to like the like actual little island.
So what is the
itself,
constant rule?
but We'll figure it
Gonna
out.
happen.
Yeah,
How old's your sister?
she's 26.
Alright,
Yeah.
the 2000 registered to stay.
That's where I should try to make Toronto before I move
And then
fully
what's
out.
gonna happen?
Yeah.
One hell of a long drive.
Yeah, exactly. That's what I was saying.
Kinda looks like
To go
this,
before
right?
we're all too far.
So what's
Yeah, I
gonna
definitely want to
happen
go
here?
there. There's just like a
It's
lot of
gonna
cool
look
stuff.
like
Yeah.
And my grandpa
I
said
will
he
be
would-
Drake.
the other side.
Yeah. My grandpa said he would go like
Okay,
because he has like
That's fun.
stuff. Like,
Yeah.
there.
so in our process, you know what our K is,
He
right?
had what I didn't like to do.
What am I gonna write here?
We could go out there for my uncle's birthday. Like a golf trip to there, but then just go out to like.
Yeah, exactly. So
Wow.
right, what we have is E to the
It's like
KX.
some-
Our K is
There's like a huge casino.
right? So we're gonna write the right
Oh my
hand
God.
side, which is the derivative of the KX.
I couldn't read it.
Put our K.
I've been there like 100 times. My mom
Yeah,
knows
exactly.
It's like a big casino. There's like 2 golf courses.
Okay.
Boys trip. Somebody like the engine trips coming up. I'm actually, I was just telling my friend that was texting me. He's freaking out. We're like both huge gold fans. It was
Treeville.
Festival, dude. I
Jake will and Drake together. I
I
actually
did.
wanted to try.
I called my mom this morning. I was like, crazy. I was like, Irvy's birthday present. You trying to slide me 300 right quick? She's like, so I'm going to Treeville Festival.
You're kidding me.
We're just gonna put in and multiply out.
How can I not, bro?
I'm so
How can I
jealous.
not
No,
know? I
I'm
know
so
this.
jealous. When I saw that, I was
Yeah,
like,
that'd be
I wanted to do so bad.
Dude, oh my God. I literally, like,
Yeah, that's fine. You can keep it in.
I hate how, like, because my friend and I do this. My friend that speaks and I be doing it. Every single, like, time, like, there's just, like, something, like, options for, like, yeah, we could do that. I don't be sit there and think we think and look at those memories. We're gonna do it. Like, Atlanta, like,
I do
we're like,
friends
man,
like that.
hey, man, it's right there,
It's right
bro.
there. It's
It was
so
like 4
close.
hours away. Dude, it's right there. We can just go to Atlanta. And then we look at each other again. We're going to Atlanta. Why should we do that? But yeah, no, like literally last night he looked over at me because I was like, when you see the lineup, he looks at the lineup, he's like reading through it, he's like, what?
I know.
And I'm like, bro, we can go. It's only 3 hours away. And he's like, we do it. And then I was like, let me go. Dude, the lineup is so crazy. Usher is the headliner with Will Durst.
I love Will Durst. I'm not ashamed of it.
Like, yeah, dude, he's gonna be there too.
I'm excited for JID.
J.I.D. and Glorilla is gonna be there.
I just love them.
I'm gonna be
Tomorrow too.
tomorrow too. I'm gonna be throwing it tomorrow.
He just put a song out with Don Toliver.
Oh, it's probably on television. But like, it's so crazy. Like the fact that like J. Cole boss, JID, and Birkin or whatever that might mean that they might perform sacrifices. They might cry. If they perform sacrifices, I might fucking cry. I'm being so realistic, because I like listen to that song religiously.
I really this opportunity. It's wrong.
It's $250. Dude, it's like $250 plus to go see Drake on the
Yeah.
I literally,
It's probably like $700.
I really gotta say no to this. Like, I'll pay for gas. I'll be like, you guys can pay for gas. Bro, I'm so hyped. I'm literally, dude, and you got so many bags.
Right, so if we do this, okay, now we're just focused on doing the derivative.
I don't know. I'm so hyped.
So 2,000, 9,000. Okay, and then we get
I'm telling you, like, your sacrifices comes on, tears streaming down my face. I'm telling you. I'm gonna be screaming my heart out.
Oh yeah, exactly. That's all you do is push the line.
Oh, so, okay, basically.
I still gotta buy the tickets, but my mom sent me money today.
Exactly. So
Hey.
this is like a callback.
Yeah.
She like sent me the transaction, like the I'm over the transfer, and it's like spoiled birthday boy. You have to like, ain't that great. At first I thought she was gonna be like, okay, I'm coming to you.
Yeah.
Like,
My mom would so do that.
that's what I'm saying. I literally.
I would not be surprised if my mom ends up coming to me.
No, I
She's
literally.
fun, so it's okay.
Yeah, my like roommate wanted me to give him all the phone when I'm talking about him. I'm like, man, you trying to go to Beerville Festival? He's like, why would you do that? I'm like,
I guess that's
City girl.
Oh no, no,
Maybe a little easy.
Yeah, that's fine.
Nah, bro.
Oh, I forgot.
Dude, I'm telling you though, like, that bad.
Do we need a little bit more time to work here? Who'd like a little bit more time? Okay, it's looking pretty good out there, so I'm gonna go ahead and review this together. Okay, so we're supposed to figure out f prime of 20, but I don't know what f is, right? I don't know what f is, much less f prime. So let's start with f. Well, what kind of function do you think f is going to be? Do we think it should be a linear function? Yeah, it should be an exponential function, right? So the first thing to do in a problem like this is, look, we're going to have to find out what this function is first so that we can do its derivative and plug in, right? So to figure out what it is, this is sort of a callback to our first exam where we got to come up with an exponential function, right? We got to come up with an exponential function. Well, we know it should have the form f0 times e to the kt, right? Where f0 is our initial investment, so that's 2,000. And then we multiply by e to the 0.08t. And then I can go ahead and start with the first part, f of 20 here, which gives me something like, what is it, 9,000? Okay, it would be 2,000 times e to the 0.08 times 20. And if we plug that in on our calculator, what do we get? 9,906-ish. Okay, so that is representing what in terms of this problem? Who's f of 20 representing? Yeah, 20 is my t, so it's been 20 years, and 9,906 is the dollars in my bank account. So after 20 years, I have $9,906 in my bank account. All right, now let's do the second part. So for the second part, we have to figure out what is f prime of t. Well, the way I'm going to do that is just by using our usual rules here, our usual rules. So the constant multiple is just going to hang out. So we get 2,000. And then we multiply by e to the... Actually, we multiply by the derivative of whatever this guy is, which the derivative of e to the kx is k times e to the kx. So that 0.08 gets multiplied in front. And then we have e to the 0.08t. We just rewrite the exponential part. So you can think about that as like this power gets multiplied down, keep everything else the same. And now to finish it off, I just plug in 20 to get 2,000 times 0.08 times e to the 0.08 times 20, which gives me, what does it give me?
792.
Okay, 792-ish. All right, so the interpretation of the derivative one is a little bit harder. Does anyone want to take a stab at it? At interpreting f prime of 20 equals 792? Noah?
It's one of the first years, $792 to be added to that.
Okay, that's a pretty good statement there. I like it. It says, so the statement was, on the 21st year, my bank account's going to go up by $792. The only thing I would add is I would probably say about $792, because that's to say basically we're doing a tangent line approximation. My bank account's probably going to go up by about $792 in the 21st year. Another way of saying it would be to say at the 20-year mark, my bank account is growing by about $792 per year. Okay, about $792 per year. That's the rate at which my bank account is increasing at that particular moment. All right, of course, we're earning interest continuously, so the rate at which our interest is growing is different second by second, millisecond by millisecond, right? It's changing all the time. But this is the rate that we're experiencing at the first millisecond of the first minute of the first hour of the first day of the year, right? Okay, any questions on this group exercise? How do we feel about that? Not too bad? Do we feel a bit better after like getting our hands on it ourselves and doing the rules and stuff? Okay. All right, then we'll move on and talk about something else. So let's see, how much time do I have? It's 3:40, so we got 8 minutes. So we do the quiz. Okay, we're gonna do another group exercise here. So we're gonna work on this warm-up problem A here, okay? So we had a couple problems like this, I think, already on the problem set for compositions. But what we want to do here is write down two different functions, f of z and g of t, such that if you compose them, you get the resulting function. So it's a bit of a work backwards composition problem, okay? So work on that, and I'll be coming around to help. And Jacob will too, and then we'll do the quiz.
I literally don't even know where to start. My brain is like...
It's like
No clue. So, okay, we had some problems already, right? In the section.
Yeah, but then it's already solved.
If I give you one
Yeah,
function,
we're going
and I give you another function, then you can plug the one into the other, right?
So you just gotta separate.
I think so.
Okay, so this is like the backwards of that, right? I say, I took two functions and I plugged one into the other. And this is what I got as the answer, right? And you see, now we're gonna ask, what is the, what are the two functions?
As per usual in this class,
The other,
right.
right? So it's helpful to sort of look at this in terms of like there's an inside and there's an outside, right? In terms of the one function which is being plugged in is usually where I like to start. So I look for something which looks like it's being used as the input in another function, right? So for what do we think for part A? What looks like an inside function? Probably 3t, right? So 3t is going to be our g of t, right? And then what's it being plugged into? Of just z or whatever, or t if you want. Yeah, you got it. I'm not messing with your head. You got the answer right away. That's it, right? Let's try to work on the second one. Exactly. So it's just whatever the inside function of g of t, right? Because f on g of t, g of t is just all of the inside. F of c
Yeah, I'm
and
like,
like right? So the input should match whatever
I would know what it would look like if I tried to make one now. Just because, like, think about how many teams that, like, should have won this season. Like,
Yeah.
that already, like, Alabama lost their fucking, like, or no, UNC lost to Alabama in the first game of the year. What was up with that?
I really like Purdue
Yeah, that's
because
pretty good.
the kid that went to my high school plays there.
They just on,
Yeah.
on their, what was it, like homecoming? It was just some special thing.
Yeah.
They had, like, lacrosse. I was like, damn.
So like I don't really know.
And some teams that are usually like locks for like getting into like the Final Four, or like the round of 8 or something.
Good to me. All good, man? Doing okay?
Oh, I guess I'll find out in a few minutes.
Definitely. Good for you. Okay.
He's probably the closest like to a famous person. But like he's there.
Oh, that's awesome. Okay, so we start off with something like an f of g of t. So there's a clear inside and an outside, right? So to identify g of t, it's as simple as looking like, okay, what is on the quote-unquote inside of this equation? Well, I would say probably this 3t here, right? So if you said that g of t is 3t and f of g of t is ln of 3t, right? So I take 3t, I plug it into the function f, and I end up with ln of 3t. What do you think f is going to be?
Oh, it's Brett Michaels, which is the guy who's like the
I take
Ezra
3t,
has
right? And I plug it in as the input in the function
he's like
f.
royalty.
And the result is I get ln of 3t. So I started with 3t. What did I do to it to get ln of 3t?
That's it. That's all we got.
Yeah, I don't think that happens, to be honest.
So what we did here, right, in this case was we just took 3t,
I just like that a
used
lot.
it as the input in natural log,
It's so funny.
right?
met LeBron James.
So when I write
in
f of z here, all
Like-
I'm
an
saying is
elevator.
change up the function. But when I write
Wait,
ln
what?
of z,
No.
I walked in
sense
the
that
night.
if you replaced
and, like,
z
walked into this elevator, we were in South
by
Dakota, and he like
G
walked
is
in after us, and I just remember
You
being
replace
so
Z by
like I was
3T, you
probably
get
like 6,
ln.
but I was so starstruck.
What?
And I just like looked up at him and was like,
That's so crazy, dude.
that's probably the coolest person.
Yeah, that definitely beats me. Damn, that's wild. That's so crazy.
I was like 6 though. So
No, but like that's still crazy.
All right, so I saw good work out there. I know these problems are super like mind-bending because you got to work backwards and come up with functions that are like you got to come up with the question after having been given the answer, right? That's sort of the way I think about these. But this skill is going to be extremely important later on when we learn the chain rule, which will be section 3.3. And it's going to be probably the hardest derivatives that we do will be with the chain rule. So not trying to scare you, I'm just trying to say that this skill is sort of the foundational skill that we need to use when we use the chain rule, which is what makes it so hard. Okay, so for this one, what we want to do is just express this as a composition of functions. So I like to start on the inside, okay, and identify what is the inside function. Well, in the first case, it's not too hard to see that the inside function should be 3t. So I'm going to let g of t be equal to 3t, and now I need to come up with a function, f of z, equals something such that if you plug 3t in as the variable in this function, you get ln of 3t, right? Well, that function is just the natural log of z. Okay, and we use a different letter in each of them just to be extra careful when we're plugging one into the other that we don't get too confused. Okay? And for the second one, there's a ton of different ways that you could do it. A popular one that I saw is 2t plus 3 for the inner function, and then the outer function should be, okay, what do I have to plug in here? What do I have to plug 2t plus 3 into in order to get this original expression? Well, that's the function 5z squared. Okay, so tricky problem, but gonna be important for chain rule later on. All right, we'll stop there and then we'll do the quiz. Huh? Yep, you're good to go.